Welcome back to this lecture series on nonlinear systems. So we'll continue our discussion on the properties of uh, that certain nonlinear systems can possess, but a linear system can never. But linear systems can never possess. Okay. So in the last lecture, we saw that linear systems and nonlinear systems distinguish themselves on the basis of the fact that the nonlinear systems do not satisfy the linearity property, while the linear systems do. But that was not the only property that we said that nonlinear systems have, which distinguishes them from the linear system. And we specifically mentioned three other properties that a linear system will never possess, but a nonlinear system might possess. So the three were finite escape time, multiple isolated equilibrium points, and limit cycles. So in this lecture, we'll discuss all these three properties briefly. Okay, we'll go first with the finite escape time. So consider the state equation that I have shown. This is for a scalar system. So x, basically this state equation is one dimensional. So x dot equal to x square. This is what I have, and if I solve it, uh, I get x of t to be equal to 1 by c minus t. Okay, and if in such a case, if c is any positive finite constant, so basically indicating if the initial state x at t equal to 0 is something 1 by c and is positive, then what happens to the solution? So let's say that x of 0 is 1, indicating that c is equal to 1. Okay, so what happens to x of t? X of t, for x of 0 to be equal to 1, x of t will be 1 by 1 minus t. Okay, now as t increases from 0 towards 1, you observe that as it comes closer and closer to 1, x becomes larger and larger, and as t approaches 1, x approaches infinity. So the state variable or the state vector here is approaching infinity. It is becoming unbounded. Okay, that too in a finite time. So for any unstable linear system, the state or the magnitude of the state goes to infinity only as time approaches infinity. The reason being the evolution of linear systems is always exponential. Okay, and because of this, as t approaches infinity, as you approach infinity on the time scale, that is when your magnitude of x will also approach infinity, will become unbounded. Okay, but for certain unstable nonlinear systems, the state vector can actually go to infinity within a finite time. And this is the example that actually suggests that this is a nonlinear system that we have in hand. And we see that as that on the time axis, as t approaches c from 0 to c, the state approaches infinity. The state tries becomes infinity, right? So essentially, we say that the system has escaped. Okay. So certain nonlinear systems, for example, this system can have the property of having a finite escape time, which is not possible for a linear system. Okay, it is never possible for any unstable linear system. Stable linear systems, of course, there is no concept of escape because the state will remain bounded. But so if the state has to escape or become infinity, then it has to be unstable system. So hence, I'm mentioning of unstable systems only. Okay. Next is the property of existence of multiple isolated equilibrium points for nonlinear systems, which is a possibility for nonlinear systems, but for linear systems, it cannot be true. For linear systems, either you have a single isolated equilibrium point or you have a continuum of equilibrium. Okay, so before we go into the multiple isolated equilibrium point, let's see what a isolated equilibrium point means and what's a continuum of equilibrium. So let's say that you have a system, you have your autonomous system whose state equation is x equal to f of x. And suppose with f of x equal to 0, you find that the equilibrium point is x star. Okay, so equilibrium point being x star means f of x star is going to be 0. Okay, now what you do is you take a set of points around x star. So with x star as the center, you create a sphere around it or a hypersphere around it as defined. So how do you choose the set? You take all the points that are at a distance of some finite epsilon from x star. All those points which are at a distance of epsilon from x star. Take all of them. Okay. And at all these points, check whether x dot is going to be 0 or not. If x dot is 0 at any of this point, then of course it will qualify as a equilibrium. Okay. Now for an isolated equilibrium, what it tries to say is, if a equilibrium point is classified as an isolated equilibrium, meaning isolation means what? Is separated from others. Okay. So you can have multiple equilibrium points, but what this isolation essentially means is, if you choose, you will be able to find such a set of points around your equilibrium point of interest, so that in this particular set, no other point except for the equilibrium point will satisfy the equation f of x equal to 0. Okay, so there would exist a epsilon. Basically, you will be able to find a distance from the x star. You will be able to define a distance from the point, equilibrium point x star, so that all the points lying within that distance from x star are such that f of x will not be 0 for those points except for the point x star itself. Okay, which means what? You are able to find a set around x star, including x star, where you are not able to find any other equilibrium point. And hence x star is in isolation. So x star becomes an isolated equilibrium point. Okay. Now, if for a certain equilibrium point, if you cannot find any such finite distance where where you will be able to say that this is actually an isolated equilibrium point, then that equilibrium point of interest becomes a part of a set of equilibrium points which are existing in a continuous manner. So they are arbitrarily close to each other, very close to each other, one after the other. Okay, and we call them a continuum of equilibrium. So linear systems can have only one isolated equilibrium point, and if there are multiple equilibrium points, then it has to be a continuum of equilibrium. It cannot be anything else. Okay. However, for nonlinear systems, it is possible for them, for certain nonlinear systems, you will see that they can have multiple equilibrium points which are isolated from each other. Okay, you cannot find this happening for linear systems. For example, when you take up example for the nonlinear systems, you will see the isolated equilibrium point. But coming to the linear systems, let's say that it is of the form x dot equal to ax. Okay, Now for equilibrium point, you need to satisfy this. A of x star has to be 0 if x star is going to be equilibrium point. Now, if there is a single isolated equilibrium point, then essentially it means that A is an invertible matrix. If there are multiple equilibrium points, then the only way this can happen is when A is non-singular. And when A is non-singular in this particular case, then you have infinite solutions for this particular equation, which essentially means that you will have infinite, you will have, uh, of course, infinite number of equilibrium points, and what you will see that it will become a continuum of equilibria. Why? Because let's say that A is non-singular and x star equal to some alpha is essentially satisfying x star equal to 0, then any scaling of this particular alpha will also satisfy the condition of A acting on the point to be equal to 0, right? For example, if you have 0 1 0 0 multiplied by x to be equal to 0 is what you want for x star to be equilibrium point. So what you have x1 can be any value while x2 is 0, which essentially means the entire, it's a set of basically the x1 axis. One can see I have not introduced what the axis in this set is. So basically it is a collection of all those points where the second state vector is 0, which is x2, but the first state vector can be anything. So there are infinite equilibrium points, and you can find that these are not isolated from each other. Okay. So for linear systems, it is, I'm showing it through some example, but one can also show that for linear systems, if you have isolated equilibrium point, then there is only one isolated equilibrium point. If you have multiple equilibrium points, then they are always in continuum of equilibria. Okay. But in nonlinear systems, in certain cases, you can have isolated equilibrium points, multiple isolated equilibrium points. Okay. So the third property is the limit cycles, which are possible only in case of nonlinear systems, but not possible in case of linear systems. Okay. So to understand this, let us consider a linear system where the two state variables are x1 and x2 and are related as shown here. x1 dot is x2 and x2 dot is minus x1. Okay. Now for the linear system, linear time invariant system to exhibit the oscillation, we need the eigenvalues of the system to be purely imaginary, non-repeating and purely imaginary. So in this is an example where the eigenvalues are plus minus j, and non-repeating, purely imaginary, and the oscillations will be with a frequency of 1 radian per second. What is going to be the amplitude? The amplitude will be exactly equal to the magnitude of the initial state vector, which is xa. Okay. Now, if there is certain perturbation in the system parameter, the eigenvalues can either fall onto the left half of the complex plane or to the right half of the complex plane, which essentially means that in the former case, the oscillations will die out eventually, whereas in the later case, the amplitude will keep on increasing. So you cannot have a sustained oscillation for all practical reasons possible, right? And the amplitude here, even if let's say that you manage to have purely imaginary eigenvalues, the amplitude solely depends on the initial condition. It is fixed to the magnitude of the initial condition. You can't change it. Okay. So this is what a linear time invariant system would exhibit. But in case of nonlinear systems, you can have oscillations of fixed amplitude irrespective of where you start. Okay. Except for at the equilibrium point of the system under consideration. Of course, because by definition, equilibrium point means if you start at the point, you remain at that particular state for all time in the future. Okay, so consider this state equation: x1 dot is equal to what we have on the right hand side, and x2 dot equal to this. If you observe closely, this is just a modification of what we had in the linear system. This minor, the modification is the nonlinear part that has come up here. Now, because of this nature, apart from the point initial condition 0 0, which is essentially the equilibrium point for this particular state equation, okay, apart from this equilibrium point, if you initiate your system at any other point other than the 0 0 point, your trajectories or your system will go towards a oscillation of amplitude 1 with a frequency of 1 radian per second. Okay, so irrespective of where you start, except for the equilibrium point, the system will finally tend towards exhibiting towards oscillating behavior, where the oscillations will have an amplitude of 1 unit and the frequency will be of 1 radian per second. Okay, so this is a very important phenomena that is, in fact, exhibited by nonlinear systems, and such type of oscillations that you see are known as limit cycles. Okay, so oscillations are essentially termed as cycles. Okay, so this is again another property that a nonlinear system cannot have, but a linear system has. So we'll discuss these three as we proceed um, with our discussion on nonlinear systems. We'll encounter these three as we proceed with our discussion on the nonlinear system in the forthcoming lecture. So we'll see how things are revealed. Okay. So uh, in the next lecture, we'll discuss some simple examples of systems which are actually nonlinear, and I would again encourage you to look for properties that nonlinear systems may possess but linear systems may not, and also to look up for some examples of systems in day-to-day life which actually can be modeled as nonlinear systems. Okay, so we'll stop here.